Good morning, everyone. I'm Jim Jachetta, CTO and co-founder of VidOvation. Today, I'm very excited to have Adi Rozenberg from AlvaLinks on our webinar, and he's going to teach us about network observability, or how we can observe what's happening in this cloud or black box of video transport. So take it away, Adi. Lay some knowledge on us.
Thank you. Thank you, Jim, for hosting me. Let me just share my screen. I'm going to try to do that. Let me know when the screen is available.
You haven't started it yet.
Are we okay?
No, we see the not the actual output, just now it's black.
Don't see.
I swear we tested this a half hour ago.
Do you see my name?
I see it's blanked out.
I would go in and out of sharing again, Adi,
Yes,
and
yeah.
that works because I saw it briefly, but then it went away.
Yeah.
Well, who's?
I see it now.
No. So, but it's the
I stopped sharing. I'm going to do it
it's not the output of the deck.
Hold on 1 second. Let me start to do a share screen. I'm going to do PowerPoint, but share. We see it now.
We see it, but it's okay. Go ahead. Yeah. So
Yeah.
launch it. Launch it. It's not it's not showing us the presenter output. It's showing us the, you know what I'm saying? You have two screens?
Yeah.
That screen's not working. Maybe switch screens.
Fine. This is the. Now?
No.
No. I'm going to kill the presenter mode.
I have the presentation.
So you know what? Let's do it like this, and let's.
No, here. I got a solution here.
You see the less graphics, but.
Yeah, go ahead.
Just once again, last trial. Now?
No.
Fine.
Jim, can you go ahead and share it? And then
Yeah. I'm trying to remember where I put it.
All right, go.
Here it is.
Apologize for the difficulties.
Here I got it. So yeah, stop.
Are we in host mode or we are in?
Yeah, stop sharing, Adi.
Okay. Well, sometimes we cannot.
Sorry, guys. It's a holiday, you know. We started drinking the apple cider the spiked cider too early. So here we go. Here we go. I got it. Here we go, Adi. Okay. Do you see it, Fallon?
Yes, looks great.
I see it. Yeah. So
it's the version without the it's fine. It doesn't have it's fine. Here we go.
So can you go to the next? So thank you very much. My name is Adi Rozenberg, and I'm going to talk about a new solution that we are providing. I'm coming from a company called AlvaLinks. I'll give you a short bio of myself. I'm a visionary and a technology leader with rich experience in developing state-of-the-art broadcast and network technologies in the field of broadcast, video, and networking. I'm the author of 8 patents on live video delivery over public internet and adaptivity in video delivery. In 2018, I was a recipient of the Technology and Engineering Emmy Award for my pioneering reliable transmission method of a live contribution and distribution TV links, me and many other people with me. I'm actively promoting the secure and reliable delivery of IP networks worldwide, and I'm a contributor to the RIST activity group for the development of the reliable internet streaming transport protocol called RIST. But I also know all other protocols in the field, SRT, NDI, 2110, and even ZigZag. Next slide, please.
Yeah, hold on 1 second. I found that was the older deck. I found the most recent one. Here we go.
Okay.
There we go.
It's the same content.
Beautiful. Do you see the next slide?
I don't see any screenshot.
Oh, let me see. Let me stand by. Here we go. Third time's a charm. There we go.
So let's talk about video over IP. It's becoming a norm. In the last 6 years, it becomes a norm as we have the spread of cloud, IP workflows coming, new protocols are coming, open source protocols like SRT, RIST, NDI are coming, and the industry moves to IP-based workflows. We are moving away from the traditional way we used to do things using dedicated fiber, MPLS, towards internet and cloud workflows. I'm not saying they are bad. Actually, I'm saying those should do that and do a combination of those as you see fit for your services. Cloud production and remote editing is challenging for everybody. The delivery network is something that many people don't look at. They think it's there, it will provide everything. But in fact, it's becoming more and more problem prone than before.
They think it's magic. It just always works.
Exactly. Like, as I just need to call the service provider, the local service provider, and everything will work. I can consume Netflix, Amazon Prime, Apple TV, and it will always work. It will never fail on me. So let's try to understand what is missing. Why is there a need for something here to make some logic or some sense in the issue? The problem is that more and more responsibilities are falling on the broadcast teams to master. Broadcast engineers that are trained in video production, taking the camera feed, taking the NFL game, suddenly need to understand things like ping, routing, cloud, CI/CD, gateways, redundancy, availabilities on VPCs, things that they did not learn.
Jitter is another one,
Jitter,
right? Latency.
Yeah, exactly. Those are new things. Network availability. These are things that pose a problem for them to learn, to master, and the technology is ever changing all the time. Every year or 2 years, we have a new protocol, a new workflow that we need to master.
We were talking before we started, Adi. You know, I'd mentioned that I hear this all the time. A broadcast engineer who's proficient at IP would say, "I miss the days where I could trace an SDI cable from the camera to the switcher, to the router, to the production switcher, to the transmission link, to the microwave link. There was a path you could trace out. It was easier to troubleshoot signal continuity. It goes into an IP switch, even in your own network. It's a void, it's a cloud, it's a black box. Once it's packetized and it goes into my facility, facility is one thing. At least your IT department has control over that. Once it hits the public internet or even a service provider, their managed cloud, their managed services, it's all a big unknown black box, right? And that's
exactly.
You help us shed light into that black box.
Exactly. So just think of it, that you take your internet cable, plug it into the switch, and then it goes to the cloud. What is the route? How it goes through? Where does it hit? But moreover, when I have a problem and it is outside my organization, whom do I call when it hits the cloud? What is the name of that IT manager of AWS, Azure.
You called Jeff. You
Uh,
called Jeff Bezos.
yeah,
I got Jeff on my phone.
So, in fact, what we see is that more and more network-related problems, identification, resolution are taking a lot of time and resources for many organizations. And we want to get rid of that. We want to save time. We want to be on top of that thing that we call the network. We can't allow it to stay like a beast, like that black box. We need to have more control. We need to have more visibility so we can prepare ourselves, get ready to be on top of problems, so that if something is brewing or happening, there is a trend, I can react to that. I can activate redundancy. I can select maybe a different availability zone. I can select a different circuit or service provider. But today, everything is done reactive. Something breaks down, and then I make the decision. But while I'm making the decision, I have service problem. I have black frames. I am suffering. The
Well,
idea with AlvaLinks.
use our automobile as an example, right? You know, some people drive around and they don't think about car maintenance, routine maintenance, rotating the tires, changing the oil until the red light comes on and there's a problem, right? We want to
Exactly.
prevent these problems.
And then you pay a hefty toll refixing that.
Because you burned out your motor now because you didn't change your oil.
Exactly. Something simple that you could have done could have
Right.
saved you a lot of dollars. So many people will ask, well, I have reliable delivery. Like I said that I'm working with the wrist. Why are there not enough? Why wrist, SRT, NDI, Quick, or even WebRTC are not enough? And the fact is that they are reactive to events. They basically react to packet loss. They react to jitter. They react to reordering. They are trying to shield the receiver against any network artifact. But they are focusing on one single stream. They don't care about the other streams that might be running alongside with them. They are not seeing that maybe there is a brewing problem from IT backup or IT operations or somebody else using the same medium like them that causing them the problem that they need to face. They need to be vigilant and see what is going on so that they can react. They can go to their service provider, ask for better quality of service rules. They can ask for more bandwidth. They can talk with the IT people or maybe their own services to get more peace of mind. The problem today is that they don't get that. They just have basic information about how many packets were sent, how many packets were received, how many packets may have been lost, how many packets were received, what caused the problem, or what are the latency changes, jitter. Usually that information is missing.
It happens too often, and luckily, you know, your wrist or the bonded cellular SST is robust enough to overcome momentary losses, but there'll be a hit, some unexplained hit, and you know, 9 times out of 10, it's some bottleneck on the public internet, or it's not necessarily the first hop of the cellular link. It's the backhaul from the cell site to the sonic network and then the public internet. So, but you don't know where this problem is happening. So it would be nice to know, like, we took a hit and we don't know why, to know that yes, it was the internet ISP at the broadcast facility. No, it was the cellular provider. No, it was the cellular provider's sonnet link or their backhaul link, etc. You can dissect all of that, correct?
Exactly. Basically, you raise a very critical point. You want to know to whom to call, whether it's the vendor, the service provider. As you have the information, it will pinpoint the problem faster and you can resolve the problem faster. You might not be able to fix it immediately, but pinpointing the problem is the first rule where I need to go and address it next time so that it will not repeat itself.
Yes. Yeah, we were talking before we started that any form of correction, whether it's self correction, you know, I need to improve something in myself, the first step is being aware of that you have a problem, and that's
Exactly.
personally, and it applies to technology. Um, um, Addy is a big proponent of running tests before the event, run tests while you're evaluating service providers, and then continuously probe and test during the event, and you can avoid serious problems on game day or during your event.
Exactly. So let's hit the next button. So the question is, how do we identify network problems and how do we prevent them? We need to get to the root cause of the problem to ensure that we tune our delivery solution and use the right network solution for our intended purpose. If you have like a 5 megabit pipe, you will not try to push 20 megabit stream through it, right?
Right.
But this, and if the pipe has high latency, you will not try to push like a low latency type of service across it.
Yeah, like
You need
constant
you
bit
need
rate, low latency, or JPEG 2000 or something like that, right? Yeah, yeah.
exactly. So IP networks, what you need to think about coming out of this presentation is that IP networks should be treated like an evolving entity that is constantly changing and evolving, meaning that what you tested today might change tomorrow. What you tested at 9 a.m. might change at 11 a.m. You need to be on top of that. And of course, in 2 weeks' time, that might change. And in 6 months' time, it will change. You need to be on top of that. Otherwise, you're constantly reactive, and that reactiveness will take time, materials, support fees, contractors. That will be a pain in your bottom line.
Well, yeah, lost advertising dollars, lost revenue.
Exactly.
Sponsors don't pay for TV shows or sporting events that are black or jittery or dropouts.
And you might lose your next account because you
Right.
failed to deliver. So what is missing from what we do now? So with the traditional workflows, broadcast solution will use multi-viewers to see how the data was encoded or received. We are using ETR 290 compliance to see how the transport was delivered. We have alarm monitoring. Those focus on content compression, transport packaging, and delivery issues after the fact. Okay. Slide the next piece.
Oh, you know something? I forgot to do our little poll. So let me see here. We can uh, let's ask our audience. Have you ever experienced, regarding video over IP, have you ever seen an unexplained packet loss, a dropout, all the things Addy discussed, jitter, black screen, freezing, even minor things. Some of our, we were talking about a customer of mine that I actually spoke to yesterday, said that I use vendor A for my video over IP transport. I never have a problem, never have a single problem. Maybe Addy's overconfidence is something to consider. You know that if you're overly confident and you think your solution is infallible, that's the guy who needs to watch out, right?
Yeah.
So you see that, yeah. Everyone says they've we're all in the same boat. We know an IP link is not perfect. So sorry to interrupt you, Addy,
That's
but
that's
we
okay.
made the poll. I wanted to use it. Fallon made it for us.
I can tell you that before going to the next topic is that I've been in touch with tier one service providers using IPs, organization that I did not even imagine that might need my services because they run a very tight shift and they have either their own circuits, their own fibers. And in fact, they were the first one to acknowledge that they do have problems, they do suffer, they invest a lot of money and the manpower in order to make sure that things like that do not happen, and they do. So they need to be on top of that, and they are always looking for better ways to improve their operation.
So we were talking about that too, that this is not just a tool for the customer, the broadcaster, the sports league. The service provider could have this tool as part of their arsenal to be proactive. So they have control over how the signal is routed. So if there is a congestion at their POP or their data center in Chicago at the moment, they can intelligently route around that to get to New York from LA, et cetera. Right?
That is correct, and that brings me to the next segment. Basically, IT solutions today, the IT solutions today basically use commercial observability tools. Here is a small list like Thousand Eyes, Zabbix, SolarWinds NPM, Datadog NPM. Those tools are used by broadcasters, service providers, circuit providers, but these tools focus on one thing: network availability, cloud resources, application users, how many users, and they do a limited sampling of the network. They do not focus on the video delivery. They cannot, in their current installation, detect transient events like jitter, packet loss, things that happen for the duration of 10 milliseconds, 100 milliseconds are not sampled, because usually they will sample the network once a second or even more than that. Now, when you test the network once a second with a packet, an event that happens for the duration of 10 or 100 milliseconds will not be registered with that one packet, unless that event is prolonging for a long time, and this is a constant event of packet loss. Transient congestion events, transient latency changes, and I will show you that in a real environment, cannot and will not be detected by these solutions. So even the service providers...
So the granularity of these tools is not fine enough to capture those 5, 10, 15, 20 millisecond events.
Exactly. Just as an example to people that in the audience, if I'm doing a ping test, I would send a packet ICMP packet every 1 second. I can make it even faster. I can send it every 100 milliseconds. That means I am sending 10 packets every second. Imagine if I'm running, how many packets I'm not seeing, how many loss events I'm not feeling. I need to have better granularity. I need to have better accuracy. I need to have something which is at least 1 millisecond or below that to sample truly what is the latency changes on a packet by packet, what are the routing changes, what are the jitter impacts, and so on. Next, we already addressed that the reliable delivery solution, I addressed that in the previous slide, GRIST, SRT, ZigZee, and DI, they focus on the jitter recovery, but they have narrow viewpoint. They focus on a stream-by-stream basis. And that is a problem because they don't see who is causing the problem, the causation. They don't see what caused that packet loss and whether they recovered that or not. I am saying we need to be on top of that. So now let's talk about what we do and what is different. AlvaLinks Cloud Rider, which is the name of our solution, provides a proactive network observability. That is a patent-pending technology. We basically run multiple tests between a source and destination, gathering more than 20 KPI tests in parallel, synchronized in time. So then now we can synchronize the events and see them on one single pane. So we can now see the correlation between events as they happen. Each test is focused on dedicated packet arrival, whether it is sent, arrived, and we can compare that on a packet by packet, incoming or outgoing between source and destination. We take that metadata, process that, and send that to a cloud database, timely cloud database for further analytics and visualization. In the future, we will add machine learning and AI to give tooltips and other capabilities that are still in design. User can see real-time data and watch historical data, which is very important. Unlike previous solutions that you have an alarm and you look at what caused the alarm, now we can see the trend. We can see that the latency has changed. Maybe the jitter is rising. Maybe the network is doing so many reroutes that those reroutes cause packet loss, latency changes. And I have some slides and then a real-time network to show you that later on.
You were telling me, Adi, actually when we first talked, me and your CEO, you showed me live that a certain cloud provider does some sort of a resynchronization or a warm reboot or refresh of all their data centers every couple of hours. Now that works fine for traditional enterprise, data storage, email, web traffic, etc. But if you're streaming video, which comes through the internet like a fire hose, even if it's a couple of 100 millisecond little hiccup, if that happens every 2 hours during a 8 hour live sporting event, that's bad, right? So you might determine, I don't want to use that cloud provider for this type of workflow. It's not meant for video over IP.
That is 100% correct. What we found, without mentioning
naming names,
what we found is that we had a customer that he thought that he had multiple diverse paths with the cloud provider. And in fact, those diverse paths basically went through the same routing core that was causing it to change every few hours and create a blip of packet loss and reroute and latency change every few hours. And that was basically the diversity. That was the idea is that if one path is suffering, I can just jump. So in fact, all the paths suffered exactly the same problem at the same time, no diversity, and they made different decisions accordingly. So now for the audience, I want you to remember the traditional workflow that you have when you're doing a sport event. Let's do left to right. We have a stadium, we have cameras in the field, whether with cameramen or they are now self-powered and remotely controlled. They will usually go locally to local encoders, and we will monitor locally the encoding quality. We will then push that to the cloud, to a destination for delivery, and we'll then want to monitor that delivery. We will put a multi-viewer, let's say, a tag as an example, or any other multi-viewer of your choice. And why do we do that? Because we want to see the delivery. We want to make sure that the delivery was okay. But in fact, what we are doing, we are checking whether the network was performing, because we in fact know that the source was pre-tested and there was no problem, no alarm came from the source. So in fact, we are trying to guesstimate what the network does. So let's visualize that. So what do we want to be on top of? So let's do some graphics animation. So let's hit a button. So basically we'll start with, let's detect the paths. We think that we have a unique path, and this is example for one of our customers that was streaming from Japan to Florida. He thought that he has two distinct, diverse paths, but our test showed him that in fact they have a lot of 2 points that are joined together. Basically, the path goes to two points that are appearing on both routes. And actually, his routes are intertwined so that he has no diversity. After learning about this, he was able to change the service provider so that he had true diversity. Moreover, with our testing, we also found out that the latency configuration that he had in his ARQ protocol was misconfigured, and he had to put some more milliseconds in order to maintain a delivery. Let's hit another button.
Here's another story that popped into my head, Addy. So, a sports network, a customer of ours, went and rented two different circuits, SLAs from two different vendors, and they found out after a failure that there was a commonality between those two circuits, that they there's nepotism. We're all sharing different data centers. And a lot of it we have no control over it, and maybe even the service provider doesn't have control over some of these things. They just let it flow as it may. So this example, it was the same provider. You bought redundant circuits from the same provider. So my point is, just because you got two different vendors, you
Doesn't
could
mean
still have this same problem, right, Addy?
exactly. And I was telling you that we found something like that just today. 6 different circuits that I will show you. 6 different circuits, all 6 circuits which are diverse geographically. One is in Europe, one is in the US. We did not even think they have any commonality other than some sources. And in fact, we found that they had a singular point that
One
was
point of
causing 1 point on those that was common. I will show you that as we will go to
in
that point.
in any engineering project, whether you're launching a rocket or a television, you cannot, good engineering, you don't
Yeah,
have a single point of
single point
failure,
of
right?
failure,
Yeah,
exactly.
yeah, yeah.
And in fact, we have correlation. We found exactly when we had the problem, we immediately could trace that and see that that specific point, that specific hop, caused the problem at that specific time, which was mind blowing. So going back to the workflow, so what we need to monitor, we want to monitor how the data leaves our organization, how that stadium. We want to focus on the streams. In this example, we have like 80 SRT streams in this capture that we monitor leaving the source. Now we want to do the opposite on the other side. We want to check how the link, how the data, how the network behaves, and what are the pitfalls. So this is like a live chart. I will show you many others that basically shows the behavior of the network. If one has a keen eye, you can see on top, you can see packet loss at the magnitude of 25%. You can see problems that arose from the network delivery. You need to be on top of that. You need to see what happened, what caused that. And we will see that in later slide, we will see things like that that explain that more in depth.
Those are pretty long events of 25% packet loss on a
Exactly.
circuit that you have an SLA that you paid for, you know.
In this specific circuit, this is an MPLS that the QoS was not set properly. Nobody knew that. And the customer, in this case, was suffering from black frames, freezes. The broadcast people said constantly the network is not working perfectly. But the IT people, they were clueless about it. And they said, we bought a circuit from a known MPLS provider, and we have the 5.9 SLA, so everything should be, in fact, okay. Once we came over and installed our cloud rider source and destination, we immediately saw this problem. And then we issued a report a day after the circuit provider basically admitted that they did not set the QoS properly for that service. And after a day, that circuit went from 25% packet loss to 0.2% packet loss, which
There you
is
go.
not the greatest, but still, SRT can overcome that easily.
SRT or anything with forward error correction or
Yeah.
ARQ can overcome that. So it was an honest mistake. Something was not provisioned right. So,
Exactly.
these live events, there's always a setup and rehearsal. So, Addy and I encourage anyone doing a live a transport over IP, public internet, or something, MPLS or whatever. This could have been discovered before the event to prevent dropouts during the event. So this could have been ironed out during rehearsal and setup instead of live at the event.
In this
So,
example, sorry for interrupting. In this example, the customer was unable to go to air, live to air, to launch new services for more than 6 weeks.
oh
That
my
means 6
goodness.
weeks of time to money
Oh
lost.
my goodness.
Okay,
Oh my
just
goodness.
imagine how much
And
manpower and money lost, revenue
and
lost because of that.
and we won't talk pricing on a webinar, but your services, it's a service. It's not that expensive.
Exactly.
You're paying, it's a fraction of the cost of what you're paying for this circuit. Why not have a tool to evaluate that circuit you're buying every week, every month?
And before jumping to that slide, I would just tell you a testimony of a customer of ours. One of our customers, with the tools that we have, he had to basically launch a service from the Far East to Europe. He basically installed we provided Docker container, installed it one in his premises, one in the destination, and he was able to pre-test the network instead of traveling from the Far East to Europe. And he wrote to us, guys, we saved more than $15,000 in travel expenses, sending 2 engineers, spending the week, finding out what is the problem. We did everything from our home. We understood the problem. That justified paying for the system. It was far less expensive. Our operation are now very happy because this has saved us some carbons, because they are very carbon-free, carbon
Yes.
emission.
Save time, money, carbon footprint. Yep.
Yeah, exactly. So this is a testimony that we got.
And we're concentrating on transport, but if you have a large facility or a multi-location facility connected with your own private WAN, you really need this tool inside the facility as well, right? For troubleshooting.
Correct.
Right. It's not
So,
just for transmission.
correct. So let's understand what we do. So we do many functions. So let's start with leak evaluation before going live. We have an event. We come a day before, or maybe a few hours before. Most organizations come at least a day before. We want to evaluate the circuits that we have. Usually we will list the service. We are not in control. Even though we may been here 2 weeks before, somebody else was in between, somebody else changed the configuration. We have to validate and test everything. So we need to do the following function. We need to do path discovery. We need to understand what dynamic path changes might have happened since the last time we used the event. What are the packet loss of each route? And this means that we might have multiple routes. The system is not tuned to one specific route. We will test all, we will discover and test all available routes so we can focus and see which is better, or maybe you will want to use bonding. We will want to discover service provider discovery. Are we using the right service provider? Yeah or nay? We want to test path RTT, path latency, path jitter. We want to discover the path hops that are truly diverse, yeah or nay. Many people do that by pushing up real encoders, but they just check whether the encoder hits the destination. They don't have the visibility about the network and how it behaves during that transmission. Now, sometimes we want to test the SLA. We want to do a step-by-step type of testing. So we want to test what is the impact of every step that we will take to discover the packet loss of each step. What is the jitter when we introduce a step? What is the RTT? Because sometimes the network is reactive. Now we show you an example where the network basically reacted to the changes and basically clamped the signal completely. And the customer didn't know about it. It was not aware of that feature in the network that he had to go and read of.
This is a good point, and I know from my bonded cellular experience that a cellular connection typically with 5G it's improving. So more with 4G LTE, it's 40 to 60 milliseconds is a typical connection, but there'll be these unexplained spikes, 1200 milliseconds.
Exactly.
but it only occurs for a split second. So you see these
Exactly.
spikes. Now, if you're a bonded cellular provider like Haivision, they actually monitor latency first, then look at throughput second. So they're monitoring those huge spikes, and what they'll do is, if the latency spikes for the moment that until it restores itself, they won't send any traffic on that path.
They
So
basically throttle
yeah,
the transmission.
yeah. But so
Exactly.
bonded cellular had to figure out, in order for bonded cellular to work, the bonded industry had to figure this out. But if you don't have bonding capability, you got no way to traverse that. So this gives you visibility of that.
Exactly. So you now with Haivision, with the AV West, this is contained within the technology. So you don't have visibility to that. Now, what happens if you don't have the solution, or you want to have more visibility so you can better tune it? That is what we are bringing forward. So maybe you want to use SRT and have throttling, because with SRT you can configure it to do throttling. Same goes with REST, same goes with ZigZag. There are ways to do that, but you need to know the landscape. You need to understand what is going on. You need to understand the history, when it happens in reaction to what. So then you can fine-tune your sender and receiver to overcome these problems, so you have a fluid service without interruption.
Well, many customers don't want to use variable bit rate. No. I have a 5 meg. I want my show to run at 10 megs, so they want to do constant bit rate at 10 megs. Now, doing that over cellular, yes, if you have a very good connection, we can get away with that. But if the pipe collapses below 10, I mean, it's 10 plus overhead, so your transport stream may actually be 12 megs. If the pipe collapses and can't support the 12 meg, you're going to lose frames. So you need the variable bit rate. But as we all know, constant bit rate always looks better, right? If you can push it through.
Exactly.
So these are the things we can probe for, test for.
So here I'm giving you some slides from our what we call a stream test, and this is 2 examples. On the left, you can see a fixed bit rate that we run, and on the right is the step-by-step. Now, one of the things that we added is that we added circuit breakers. One of the things that we are worried about coming from the industry is that we don't want to cause any harm. So we need to have some circuit breakers, so that if by any chance we hit a level of packet loss or latency that might harm other services, my services that they are running alongside with me, I don't want them to inject too much packet loss. So the circuit breakers are there to stop me midway, so that I will not cause harm. I can't have a human in between to make the decision. I need a machine to run a circuit breaker to stop that test, that evaluation, when it happens, by any chance it might cause harm, and something like that might cause harm if you're running services and you are not aware. So this is important, and it is in the technology.
So
let's see.
let me see if I understand, Adi. So in the example, I have a 10 megabit per second stream going through my circuit. Alongside that, you're running a 1.1 megabit per second test stream. Is that what you're doing?
No. So let's do it like that. Let's say I have a pipe which is 40 megabits.
Okay.
And I'm running my service. I have running 2 services. One is 10 megabits, another one is 10 megabits. Now I want to test the network, and I want to introduce another 30 megabit stream, which if we do the math, 50 is more than the pipe capacity of 40. The idea is that if I'm not aware of the bandwidth, the available bandwidth, I'm engineer that I did not read the contract that I have, in fact, 40 megabits, and I'm pushing that 30, it will oversaturate the pipe, and it will basically cause damage to the 2 services that are running. I need to stop that ASAP. I can't wait a minute or for a human to come by and stop me. I need to stop that. Even if I'm doing step by step, so I will start, let's say, at 1 megabit, go to 2 megabit, but there will be a point that the introduction of more and more bandwidth will cause harm to the link, I have to stop before it causes harm to those two services that are running. I don't want to cause any problem. Of course, if there are no services running, I can do whatever I want. I can oversaturate.
Right. You're doing a test before the event, but while you're live, you don't want the testing probe to interfere with the live show, and then back. So it's instantaneous. You see
Exactly.
a bottleneck, and you shut off for a split second, a fraction of a second.
Yeah.
Very cool.
Now, usually when we're running our Cloud Rider technology on a continuous service, we usually will consume about 1 megabit. We will send about 100 packets, give or take, plus some more for path discovery, which is about 1.1 megabit in total. So that is like running over the headroom that you usually have, and we're running back and forth to test the link, ingress and egress. So let's see a real. Next slide is from a real location, this is from a real stadium that I will not name, but in this case, on the left, can you see my mouse? In this case, the customer had 7 cameras installed. He wanted to introduce the 8th camera, and every time he introduced the 8th camera, the entire circuit went down. There was a clamp that basically brought the entire service down anytime he introduced that 8th camera, which was about 20 megabits. So in fact, he had our agent there for testing the network, and we told him, let's try to do step by step. So he said, okay, let's try to move 10 megabits. So that's what you see on the left side with the mouse. Basically, as soon as we started to increase the bit rate, suddenly the clamp came, and you can see immediately the impact. Packet loss, error rate went to 25%, and when we tried to push further, it went to 50%. Look at the RTT jumping sky high, from almost 0 to 200 to more than 200 milliseconds. Buffer emulation is a feature that we have that basically takes into account all the packet loss, latency, RTT, and basically gives the user a number that we believe if his buffer is set correctly, we'll be able to overcome packet loss. And here we are jumping from 0 to almost 5,000 milliseconds in this case. So basically the system stopped itself. You see here a sharp dive in the test because the system stopped itself and said, we are causing harm. Basically the system was said that more than 25%, shut it down. So then we said, let's do that gradually. Let's find where that limit comes. And we did the 2 megabit by 2 megabit increase. And we found out that here, at 8 megabit, there is a clamp. Meaning that the system was rigged, the network, the router was rigged so that when they cross a certain boundary, it will clamp the network completely.
That sounds dangerous, you know.
But it's normal because somebody said.
But you paid for that bandwidth, so they're giving you extra headroom that you didn't pay for. So you need to manage that. So is this the event here, Adi? I got the red pointer.
Yeah.
So this is the event happening right here. The 8th camera was added. You see it even almost goes above 50%. RTT looks like 300 milliseconds buffering, and then your analysis shut off. Is that what we see here?
Yeah, that is the circuit breaker coming on.
Circuit breaker hit, and then we backed off, and then here you're slowly probing again to try to
find that limit.
Here, maybe the customer turned the 8th camera on again. That's why we see this big spike here.
Yeah.
Okay, and then here you're probing.
Exactly.
Very cool. Very cool.
Basically, this is a real testament of what is happening. You need to be aware. People come to an event, they are not in control of the circuits. Even sometimes they even own the circuits, but they don't know who was there before. You need to test. People know, production teams know that they need to test, but they don't have the adequate tools to do that. So let's go for the next slide. So continuous path exploration. what we need to do is that when you deploy an AlvaLinks agent, it will start to do path, discover the path. It will look for all the available options to reach from point A to point B. All the available mediums, whether it's LAN, WAN, satellite, whatever it is available, we will try to discover that and continuously try to discover that. People might know traceroute. This is like running traceroute, but on steroids. Now, the problem with traceroute is that traceroute is based on ICMP ping. And ping, when they're running ping over a network, it will propagate on a different way than a video stream will. So we need to do something which is basically using UDP session-based. We basically listen to the video session and try to run as if we were, in fact, a video packet running on the same session, trying to detect the hops that the video might take. Now, what that gives us is that when the network is going over load balancers, cloud, we now can discover NAT devices, load balancers, and continuous changing of the network. One thing that we were able to establish and find is that once we're talking with cloud, the cloud ever changing all the time. It's very diverse. So, but the same can be true on data centers data when you have BGP changes and so on.
So you mimic your test payload or your test stream mimics a video stream by being UDP, just like a video transport.
Not only UDP, but UDP using the same session parameters as your video stream, but without confusing the receiver.
Gotcha. You have your test payload, not your video payload.
Exactly. So what we do is that we provide at the end of the day rich UI with correlated time-based charts for doing event zoom in and out. You can see real-time data, historical data. We focus on what matters for video delivery. What are the problems that you need to be aware of? Now, we don't talk in a video lingo. We try to talk in IT lingo because at the end of the day, IT problems will be solved by the IT people, the IT teams, and the service providers and the cloud providers. They understand IT talk, but we need to give them the information, accurate information, so that they will understand. We can't tell them we have black frames. They don't understand what is a black frame, what is cause from, what is the causation. We need to talk about in TTL, RTT, hops, the same lingo that an IT team member will understand because that was how he was trained to. This is an example that I showed before about that diverse path that we discovered. Basically, the system running discovered multiple paths and that they were using exact 2 points. And you can see the difference between the top and the bottom. You can see that they look different, meaning that the path from Japan to Florida is not exactly the same as the path back. This is another thing that I will show you later on.
Well, yeah, most providers have return video of some sort, program video going back to the event, teleprompter going back, and we were talking about this before we started. I think in our mind we visualize a straight line. It goes very cleanly. Japan, a data center in Honolulu hits California, hits Texas, and goes to Atlanta. It's not a straight line. It's not a even on a managed circuit, right? You think, well, I have a managed connection. The public internet, I would expect this, not a managed connection.
I will give you a crazy example. I was talking it was at NAB this year, NAB Vegas this year. And I was showing the system to a customer, to a potential customer. And we had that flat line, okay, which was like 22 hops, which is standard, which is okay. Suddenly the system, which is ever running, it's continuously running, bringing information, updating. Suddenly the screen goes black, meaning that suddenly we see 200 hops. We see crazy crazy scenario. We call it an elephant trap. It's like a mash of points for 5 minutes. And I'm starting, oh my God, there's a software bug. Something that can't be. No way.
It's not possible. It's not possible.
It's not possible.
You thought the tool had a bug. It's
The
not
tool
possible.
has a bug,
yeah. Okay.
Yeah. But we did draw the information for somewhere, right? We can't just push bogus information. 45 minutes later, I'm getting an email from my data center saying to me, oh, we had a network problem that caused us to go to different location, and that slowed down your connection. I said, I saw that. I literally saw that happening as I was demonstrating
in
this
real time. You saw it happening.
Yeah. And it's like you need to be a believer to see that. Sometimes you see problems that you say that it's unimaginable that I will have from 22 to jump to like 200 hops. That's unimaginable, but it did happen. I wish I could have it in video.
Or even on a smaller scale, I'm expecting a direct circuit from Paris to Atlanta, and instead it's going the other way around the globe with 22 hops. Yeah. So you assume that the obvious is that it's a simple connection.
So let's jump next. So here's an example. For instance, we have here 2 paths, same, basically going left to right. Top, we see a straight line. The return has load balancers. You can see in green there is a change, meaning that the path will divert itself, and then it hits another load balancer, meaning that it goes from one service provider and jumps to another one, and they have another load balancer. And what does that mean? That means that whether your return path, or maybe you're doing like an SRT ZigZag, your message back about the problem will be stalled down. It will slow down. So you might need a bigger buffer to accommodate, because the network is not at the same latency or distance as you might think.
Right. On the return leg, I talked about the example of video coming on the return leg, but ARQ is coming back, or the ARQ requests are going the opposite direction. And if the ARQ request is delayed, as you said, Adi, we got to increase our buffer. And
it's not only the ARQ, but let's say you have a remote control. Maybe you are running a remote NDI camera, and you need to control it with the TCP. While we are measuring that in UDP, the TCP, any TCP circuit, and we can trace TCP.
Or I'm shading the camera, and now there's a little bit of, this would cause a little bit of delay. My camera control would stutter. I'm moving left, it doesn't move left right away, or I'm changing iris. So very cool, very cool. And while this is happening on the return leg, the outbound leg was fine. It's a different path. It's
exactly.
It's like it's a different circuit.
Exactly. So let's go to the next slide. So then we come to what we are doing, which is a continuous stream delivery performance. We are testing the link. It's not in the previous slides, we talk about evaluating the link. We're going to a new location, bringing new service. But we also need to be on top of the circuit service as we are running on our 24/7 operation. We need to be on top of packet loss, jitter variation, route changes, all the same problems. We need to be on top of that. But not only that, we need to be vigilant and detect any other IP flow that either we generate or somebody else is generating, or using the line that we can detect, that may cause problems. We had cases that IT did a backup, and I had slide deck that I showed that a year back at the NAB IP showcase, that we had a problem that was caused by an IT backup operation that consumed more than 200 megabytes of my video traffic, and that caused packet loss and latency changes. But then we may want to focus on our video. We want to monitor the video, how the video behaves. So we can then select specific flows, and we can tell the software, we want you to focus on those flows, either at the source or the destination or both. Please monitor them on a packet by packet basis. Now, we don't touch the content. We don't do ETR 290. We don't do video decoding. We look at the IP. We look how the IP behaves. In fact, one of our customers is using a multicast workflow, and he wanted to make sure that his source multicast and the free destination look alike. So we did that exactly, and he was very surprised. We put a flow monitor on the source, and we were installed on the destination. We put a flow monitor on the destination, and we can compare and show him how the flow, the multicast flow, from the source, how it is received on the other end, what is the differential. You can trace the latency, the different arrival time of the multicast. And in fact, what we found that was pleasant to see is that the original jitter that he was outputting his multicast was even lower at the receiver, meaning that the network basically smoothed and improved his jitter performance as the multicast was received on the destination. So meaning that we can now focus on SRT streams. Everything has an IP, what we call in the industry 5-tuple characteristic that we can trace and follow. Of course, we can generate alarms for the events, so we can then send emails, notification for third-party tools, put that on the web UI, and so on. Any question before we go forward?
I think we're good.
Okay. So let's see some examples, and this is a very important example. This is a view of real-time capture with historical data. In this case, the customer came to me and said, look, we had a major problem that we have an alarm that happened a few hours back, and we need to see what happened to the network. Now, we don't know what happened. We run standard IT tools, and we couldn't find the problem. So he said to me, he dialed me the exact hour. I went to our database. I dialed in the range to see what is happening. And here we could see that at 7:04:20, that was in local time, the network has changed. You can see here the RTT and the buffer emulation, and there is also the latency that we don't see, has changed. And that change caused packet loss that was beyond the protection level that we had, that caused ETR 290 events to happen. But the network change also, the latency has changed completely on that network. Okay, meaning that his buffer, he was using an SRT in this case, was inadequate to fulfill full-blown packet recovery because he was trying to run a very low latency buffer, and meaning that he basically failed. He tried to run 120 millisecond buffer, and as the network changed, basically he started to get hits. And you can see here on the graph itself, you can see those small spike hitting that beyond the 100 level on the buffer emulation.
Yep. Right here. Yep. And then there's there's a hit right there.
Exactly.
It all kind of correlates. Yep.
Exactly. Once they basically cross over the 120 millisecond, he got hits on his SRT. So we were able to correlate those events and basically tell him, look, all you need to do is increase your latency buffer. Can you increase that from 120 to 200? And in fact, eventually even change that to 700 milliseconds because we were able to find even bigger events that he didn't even expect. But the idea is that this is the causation, this is the ability of the network to identify network-related problems. He constantly thought that the problem that he had was to do with the vendor and the SRT protocol.
With the bonded cellular products, it is a little bit of trial and error. If we see packet loss in the payload, in the video and the audio, we increase the latency, and it's kind of you need a human being to do that, to we can't run
Limit of
at
that.
yeah. Our modern products can go down to 250 millisecond buffering even over cellular, but that's pretty aggressive. 5G
Yes.
connections can handle that. So it's kind of like trial and error. You need to test it. So this is a much more scientific way to you can actually see that the buffer is full and figure out why, and make an educated decision on the setup of your transport stream.
Let's go to the next slide. This is another example, the same customer. I will issue a paper about that and we will circulate that. We had 4 diverse paths that we thought that are truly diverse paths. Not only that the customer used 4 different data centers and the circuit providers, but everything was designed for redundancy and redundancy. So if there is an event, at least one link will survive and will not see the problem, or it will be time difference. But in fact, what we could see, and you can see the difference, this is exactly the same time. Actually, I had 4 of those, but it did not fit the slide deck. And you can see the difference. It's exactly the same event happening, causing problem exactly at the same time. Slightly different impact on every line, but it's happening exactly at the same time.
It's similar, but yet different. And these are 3 independent circuits. And is this the connection that you found the commonality, the single point of failure?
This is, I cannot go into details, but there is a
You're under
common
NDA. Okay.
That is, I am under NDA. There was a
Gotcha.
commonality here that we could not basically, but the thing that I want the audience to see is that the ability to detect and correlate it's not only that you say, oh, I have a problem, I found a problem, I have maybe alarm here and alarm here. I need to have the tools and the evidence to see that. I need to see what has changed or what is correlate link A to link B to see what happened. Not just to say I had alarm on A or an alarm on B. I need to see the difference. What if they are time synchronized, then something is wrong in the setup. Now I have the tools and the means to go and figure out what do I need to do. Before the correlation, this specific customer worked for more than 8 weeks to figure out what is going on. He didn't have that smoking gun. This is the smoking gun. And that event happened time after time. Look at the magnitude of the event. It is like more than 80% packet loss.
Yeah. And it was very frustrating. You have no visibility into this black hole. I'm doing everything right. I have 4 redundant circuits. This problem shouldn't be happening. And you were able to shed light, observe this in real time to shed light on the problem.
Exactly. And how do you basically let's dive into the information. Let's dive into the graphs and understand how do we see that. In the middle, you see the RTT. You see there is a hit on the RTT, meaning that something slowed down that measurement of the RTT, meaning that the network has changed significantly, that the RTT gets a hit. So there's a deep depression in the RTT. You can see on the lower chart, you can see the Cloud Rider packet rate, which is the test stream that we are running. Basically, it shows that
it collapsed. The pipe collapsed.
Exactly. In this case, the network ran through a BGP reconstruction, bandwidth reallocation, and that slowed down our stream that we were constantly pushing, even did that twice. And it also did that on the RTT, which is not in our control, meaning that the network latency has changed. In this case, it's changed for the better because you see that it is lower, meaning that suddenly the network was faster. Lower RTT means the network is faster.
It seems counterintuitive, right?
But here
if the circuit collapsed,
But it also blocked many of the packets to go through. And that is the problem. Okay. So here we can correlate events.
Very cool. Very cool.
Let's go forward. Let's see if we have more
Yeah, I
slides.
think that's it. So how does VidOvation or how does a customer deploy this? What are the different? We discussed this. I know the answer to this question, but tell our audience how do we deploy? You mentioned a Docker
We
is
provide a
one.
Docker container that you basically can download from docker.hub, and then you contact Jim to get a certificate that you then load the instruct. Basically, you can download that from the web. You download that once you have a valid license or agreement with Jim and AlvaLinks, and you can install that. We in parallel deploy a cloud frontend and backend and database in the AWS environment, so
In the
that you can
cloud,
have
yeah.
in the cloud, so you can have web UI to get that, and you can run with it. As I said, Docker container. If your devices do not support Docker containers, which many old devices do not, you can put that on a Windows PC, run it on a virtual machine that can run an Ubuntu, and then it's Docker friendly. Or you can take a low-cost NUC, Intel NUC, put a Ubuntu. It costs you $0 to install it, Ubuntu NUC, and then you put a Docker container, or we provide support to install that, connect that to a local switch. You are up and running.
So the Ubuntu physical machine or the Docker all communicate to a cloud instance of AlvaLinks software, and that's where the data is stored. That's where that's where the analysis happens. So a customer could have hundreds or thousands of these probes, as you call them, all streaming, all sending data to the cloud in real time.
Exactly.
Yeah, I think this is something we've all needed. Does anyone have any questions? I know it's the day before Thanksgiving. I don't see any questions. So I will probably won't happen till next week, but next week we'll publish and transcribe this whole session. This is some really great information, Adi. I'm hoping to book some discovery calls, some demo meetings with some of our customers. We haven't officially announced the AlvaLink solution other than this webinar, but the customers I've talked to are like, "Oh man, I need this. I need this. I hope it's not too expensive." And it's really it's a great value, and I think it's one of those necessary tools that we all need in our toolbox. Correct? Very good. Very good.
Do we want to do a live demo? Let's connect to a system.
Yes. Yes. Oh yeah. Yeah. Yes. Let me give you back camera control. Hold on. Let me stop my share. Now you should have share back.
Let me try to share. Maybe it will work this time. Hold on. Okay, here it is. Let me know if you see the screen.
Perfect.
You see the screen? Excellent.
Yes.
So
Yes.
so just take the mouse here. So this is a system this is demo system that we've been asked to run on 3 different public cloud environment. We have AWS, we have Google Services, GCP, and we have Azure. We also have 2 data center locations, one in France, one in Strasbourg, which is near the French-German border, and one in St. Louis, the gateway to the West. And let's take just here. I'm checking. This is a live. I am not generating traffic. So in this case, let's look at St. Louis to Azure. We can see on top that the network already has a load balancer. The reason why the lower connection has no port is because Azure obscures make the path, but we will still see what is happening. So let's jump in to the link and let's load the data. Oh, that's nice. So what we can see is that if you can see the data, we see that a constant error rate of almost 8% happening right now between St. Louis data center running on Cogent circuits to Azure. You can see that the hops are changing. you can see that the hops changing. Basically, let me just zoom in slightly so we can have better view. You can see the correlation between the hop changes and the RTT, meaning that every time the hop change, the network rearranges itself, meaning that it will perform better or worse, meaning that the RTT and the latency will change for the better or worse with those changes, so that probably creates that high level of packet loss that we see. Okay, we can see the latency here. The latency changes and spikes, meaning that this is below, you can see the constant average latency, but we can also see average changes, which are almost 100% in magnitude than the standard latency, which once again, if we are jumping, that creates jitter, that creates packet loss that we will need to overcome. So if we are using, if we were to use SRT, I would recommend to use a big buffer and multiple retransmissions as an example. Let's just check another one. Let's do AWS to AWS just for kicks. Okay, let's see AWS Virginia going to California.
So what you're doing there is you're just clicking on that segment, bam, now I'm looking at that negnet. From the
Exactly.
graphical high level, boom, I can go right in and see.
Exactly. The system collects the data all the time and just going through the web UI, seeing real-time data. You might see that we will come here and the network will change because we discovered a new path. And look at this phenomenon. One agent is in North Virginia, one is in North Carolina. Look at the difference in the number of hops. The make of the top one is shorter than the reverse path. Look at that.
Interesting. Interesting.
Okay. And look
And
at
we have no control over that. AWS may not even have control over it.
Correct. But we need to be aware of that, because if we want to use such a circuit, we need to test it to be on top of that, so we will know.
Set our buffering intelligently and
Exactly.
and our
Without
cool.
mouthing anybody. Today, if you want to do a stream to AWS circuits, whether it's SRT or ZigZag, you are on your own. You have no tools available to test, to know what to do. You have rule of thumb rules. You need to be on top of that. You need to make your service successful. In this case, for instance, our advice is that testing the network, you need to have a buffer which is at least 300 milliseconds, so that
right.
you will not.
But you want a little headroom in case, you don't want to set it exactly to 300. So maybe you want to set it 10%, 25% higher than that, or 400.
Exactly. Now, if you want to validate whether we are bullshitting you or not, remember the old fault error correction technical recommendation that said, for fault error correction to work, you need at least 120 milliseconds of buffer based on East Coast to West Coast buffer size. Yeah, this is that exact number. You can see that 121. That is us testing the network and saying that based on the network conditions, that is the buffer that you need to do. That is what we are saying, that when there is no that much packet loss, but you definitely need to be on top of that, because you have events that the network is jumping and you need to be more than that. But that is just to show you.
Yeah, and then if you put your mouse right on that peak, you get the exact number of what that latency is. You move your cursor to, you can move 239. Yeah.
You can do a full page. You can watch it like this. If you want
I'll
more
get really fine resolution.
You can extract that as a CSV, as a PDF, all the standard things that one might expect. Okay.
Very cool.
Let's look at just for the kicks. I'm just having fun. I don't know what this is, a live system. I could not prepare it, so I'm just having fun.
Let me see my.
Look at the opposite, the path back. Actually better than the one going.
Yeah.
So basically, you need to be on top of things to validate your network. I'm just trying to find a curious link. Let's take France to Google. Let's go from France to Google. Let's see that one. Oh, that is like great. This is like more.
Oh, look at that. So one path is clean, but then there's a multi-hop path.
Yeah, exactly. So you can see here spikes happening. I'm just playing.
And we're not saying anything good or bad about Google or
No,
AWS. It's just telling you how to set your parameters, your buffer size. You go in instead of guessing and changing that buffer depth by trial and error. We can do it intelligently.
exactly. This is not a system. If one would want to connect from France to Google, it will try to connect to the nearest Google availability zone. All I want to show is that look at this long distance, look at the problem that you can see. That is why we are demonstrating that. So now I'm looking at Google to AWS, and once again, we see problems. We see buffer emulation changing, all the things that you can discover. You can look at, in this case, we're looking 1 hour back. We can look at, let's say.
But that circuit is usable if we increase the buffering, right?
Exactly.
Or if it's bad enough, then we can determine we don't want to use
Exactly.
that provider or that segment.
So right now I'm giving you the way to look at 6 hours. Let's see what happened in the last 6 hours, how good it was. And immediately you can see, well, the jitter has changed. Look at how the network changed during those 6 hours. We had some kind of a major event happening. Okay. And that event was because the network has changed. You can see that definitely the jitter went from a high value to a lower value, meaning that the network between Google to Azure was optimized by somebody. It caused an event, but now different condition can go bad, worse. We don't know. We need to be on top of that. That is the message.
And then, like you said, historically, so it's the day before the event, some rehearsal. We run your test 24 hours, and historically, we can see where the peak of the RTT hit, where the peak of the jitter hits, or where the peak of the buffering occurred, and then we know. Okay, I mean, it's not a crystal ball, right? If the event is 7 days from now, things could be drastically there, but we got a pretty good probability of a historical snapshot of how to set up our circuit.
Exactly. Basically, people have the tendency to test once and hope for the best. So what I tested now might change. We need to be on top of that. If you tested the network now and it's at 18 milliseconds, it might change, jump to 100 milliseconds in an hour. If you are not aware of that, you will fail. Your service will fail. That's the message. You need to be on top of things because they are definitely changing.
Here's the thing I thought of too. I'm a sports league, a production truck, and I'm going to the same venues several times throughout the year. I can look at my historical data from last event, last year, and kind of make an intelligent decision of what's the worst I've seen in the last year, 2 years, whatever. If you have that length of historical data, and then if some anomaly does crop up, that data is stored for the next time so we can make sure it doesn't happen.
Exactly. You can
Very cool.
compare,
Very cool.
You can make decisions, everything. And you can
So
test.
so I was telling Fallon's in our marketing department. She set up the webinar. It's like, Adi only has 14 slides. It'll be about a half hour, 45 minutes. I swear it won't be one of Jim's usual 90-minute webinars, but I'm a geek for this stuff. But we could do this all day, Adi. But this is great stuff. Let me bring back up the if you could stop sharing. Let me just bring up the here, I can take it back. Let me bring up the closing slide here. I need to drag you over here. So if any of you folks need to contact us, oh, it went to the beginning. Sorry about that. Let me do this differently. Sorry. My producing skills are a little off today. There we go. And let me share. Hmm. I'm not seeing the right screen as an option. Well, so you contact VidOvation. We've just started our partnership with Adi and his team. We're real excited. I think this is a very important topic. Um, Certainly reach out to me. There's my email address, our phone number. I can be reached at jimj@vidovation.com. You can call 949-777-5435 or visit our website. Adi, thank you so much. This was a lot of fun. I definitely want to have you back again. Maybe we can do a deeper dive. I'm sure we'll be doing demos in the coming weeks. This is a real hot topic. Thank you so much. And everyone, have a good Thanksgiving. Thank you, Adi. Thank you, Fallon. Have a
You,
good
Jim.
holiday.
Thank you, Fallon, and have a great weekend with family and
Yes.
friends.
Likewise.
Yes.
Likewise. Good job, guys. Chat later.
Thanks, Adi. Thanks, Fallon. Bye-bye.
Take care. Signing off.